Without any further ado, I'll introduce Dr. Ashley Smyth. Ashley is an assistant professor in soil and water sciences. She's located down at the Tropical Research and Education Center down in Homestead, south of Miami. Her research focuses on sediment biogeochemical processing and understanding how humans modify the structure and function of coastal ecosystems. Ashley has her PhD in marine sciences from UNC Chapel Hill, and she was a postdoc at VIMS and also at University of Kansas before joining the UF faculty in 2017. Ashley says since moving to South Florida, she's found an appreciation for coubertin and for the tropical fruit mamey. So with that, and she might share some with us at some point when we all get back to campus, but other than that, I'll give the floor to you, Ashley. Thanks so much for speaking with us today.
Great. Thank you guys for having me. Let me share my screen. Okay, everyone can see my slide okay?
Perfect,
great.
Yeah.
Just hide you guys. Thank you all for coming to my talk today. The last time I gave a W3 seminar, I talked about oysters. And I know that many of you who are out here in Zoom land or on YouTube probably know of my work about oysters. But as I started to put this talk together, I realized that seagrasses are actually a really common theme from my work. And I'm excited to share some of my previous work as a postdoc at the Virginia Institute of Marine Science, and then some new work I'm doing down here in Florida Bay with colleagues at FIU, looking at climate change and seagrass ecosystems. There are a number of people who have contributed to the work I'm going to talk about. I just want to acknowledge a few of them up front because there's a chance that I might say I throughout my talk, and it's never really just me. I am really grateful to all of the supportive and fun colleagues that I've had at UF and within the scientific community. A few of them include Laura Reynolds, John Lefchuk, Charlie Martin, Ken Moore and Emily French, and then Bryce Van Dam, Mary Zeller, Katie Hayden, and Chris Lopez. Just to kick this off, seagrasses are going to be the star of our show today. And I just want to make sure everyone knows right away that I am not a seagrass ecologist. Rather, I'm a biogeochemist who collaborates and works very closely with seagrass ecologists. I'm really interested in the role that habitats like seagrass beds, oyster reefs, have in cycling of nutrients like carbon and nitrogen. These exchanges of nutrients between water, sediments, and air are really what I'm looking for in all these different habitats. And then I put this into the context of how human activities are changing these exchanges and this cycling. This is important because there's been an explosion of human impacts on coastal systems. Human population continues to increase. I have here in figure A, a slide showing population growth in Chesapeake Bay watershed over time. We can see that there's this upward trend. There are more and more people in the Chesapeake Bay region. This trend is also true for the global population. The other part of this is that there's an increase in fertilizer sales. That's what's on this bottom graph here. Nitrogen fertilizer is in red, and then phosphorus fertilizer is in blue. We see that, so as the population is growing, we're seeing more and more nutrients like nitrogen and phosphorus. And this is because of this connection between the need to feed our growing population and the need for fertilizer to do that. So human activities have actually led to a more than doubling of the amount of nitrogen in particular that cycles in our ecosystems. And that's through the creation of synthetic fertilizer and also through fossil fuel combustion. When we have too many nutrients, though, there are negative consequences, like eutrophication, which is an image of what comes to my mind when I think of eutrophication is over here on this slide. The term eutrophication is the increase in organic matter in an ecosystem. Over the past several decades, we've seen massive increases in eutrophication in estuaries and coastal zones globally, leading to widespread hypoxia, anoxia, habitat degradation, habitat loss, consequences for biodiversity, food web structure, and the list goes on and on. In Florida, we're used to hearing terms about like harmful algal blooms, whether that's turning waters guacamole colored green or tomato soup colored red. So eutrophication is the increase in organic matter, but it's usually caused by too much nutrients, and it's considered nutrient pollution that drives coastal eutrophication. This eutrophication is a global problem. And in the US in particular, 65% of all estuaries are classified as having some impact from excessive nutrients and linked to eutrophication. When we have too many nutrients, we have those algae blooms. As the algae die and are decomposed, this process sucks out oxygen from the water column, leading to areas of low oxygen, hypoxic and anoxic conditions. We also see a lot of turbidity when we have these blooms from the algae itself, and then also other sediments that can reduce light availability for the benthic habitats and overall reduction in habitat quality. This image at the bottom of the slide is from my colleague at NOAA, who actually evaluates the eutrophic status of coastal systems and estuaries. They use 5 different indicators to assess the status of a system. That includes the submerged aquatic vegetation coverage, the chlorophyll A in the water column, the presence of toxic blooms, the presence of macroalgae, and dissolved oxygen. So when you have a system that has few symptoms of eutrophication, it's healthy. You have high oxygen, a little amount of chlorophyll in the water column, healthy benthic habitats, in this case, the seagrasses. There's no macroalgae around. And then as you get more and more eutrophic, you start to see more and more symptoms expressed, and this decrease in that seagrass biomass and oxygen. One of the consequences of this eutrophication is then habitat loss. Now, eutrophication and the nutrients that are associated with it don't cause habitat decline directly, but it's those changes in the chemical environment that do, leading to that loss of these benthic habitats, especially those that are really susceptible to low DO conditions. So essentially what's happening is that human activities are leading to the simplification of our coastal landscapes. Where we used to have oyster reefs, we now have flats. Where we used to have seagrass beds, we now have subtidal flats. And this loss of those structured habitats has real impacts on us because these habitats provide a suite of ecosystem services. These benefits that we get from the environment include fisheries, carbon storage, shoreline stabilization, and water quality improvements, including nitrogen removal, which is important because nitrogen is part of the problem leading to this habitat decline. Many of these structured habitats that we are losing have implications for this benthic pelagic coupling that happens in coastal systems. So that's the connection between the water column and the sediments. Benthic pelagic coupling is an important characteristic of coastal systems, and understanding the linkages between water column primary productivity and then sediment metabolism is really important for thinking about and understanding the ecological role or status of systems. This is really relevant for my work, in particular in relation to denitrification. Sediment denitrification is affected by what happens in the water column, what's in the water column, and then how connected what is happening in the water column is to the benthic environment. Denitrification is related to this ecosystem service of nitrogen removal because it is a primary way to transform nitrogen that was contributing to algal growth and turn it into N2 gas. So I think of denitrification as being a natural nitrogen sink. It's mediated by microbes, denitrifying bacteria that convert that usable form of nitrogen, so that nitrogen that led to the algae that caused eutrophication, into inert N2 gas. N2 gas is where we want nitrogen to be. The majority of our atmosphere is N2 gas. So getting that nitrogen back to that form is really beneficial. For denitrification to occur, you need 3 things. You have to have nitrate, which is the terminal electron acceptor, or basically, because denitrification is basically respiration using nitrate rather than oxygen like we use. You also need carbon, which is that energy source. And then it's performed by facultative anaerobic bacteria. So you need low oxygen conditions for denitrification to kick on. Because denitrification is so important for removing nitrogen, there's growing interest in restoring habitats for this nitrogen removal benefit. We see this a lot with oysters, but if we look at the historical record, as Grace Brush did in her 2005 paper, we see that to really reduce the effects of modern nitrogen inputs, it's necessary to locate and enhance these denitrifying areas throughout the watershed. Areas that have high rates of denitrification are also those habitats that we've been losing, like oyster reefs, like seagrass beds, like marshes. So it's this context that I put my work into. And so today I'm going to talk to you all about identifying which estuarine and coastal habitats are hotspots for denitrification, how climate change may affect denitrification, and then some new work that I'm kind of geeking out on right now about feedbacks between the denitrification and carbon sequestration. I've outlined this talk into 3 parts then. The first is hotspots for denitrification. How can we find them and what do they mean at an ecosystem scale? How might climate change then impact the denitrification service of these hotspots, including seagrass meadows, and then how multiple services interact. So let's get started. To find hotspots for denitrification, we need to measure denitrification. This was really the focus of my dissertation work, where I went out and measured denitrification in a variety of different coastal habitats. This is that information that we need to assess the nitrogen removal capacity of the individual habitats, evaluate that ecosystem service of nitrogen removal, and then it's also important if managers want to restore the nitrogen removal capacity of a system to know what habitats are denitrifying and removing nitrogen. I looked at 5 major habitats in coastal North Carolina: subtidal flats, intertidal flats, seagrass beds that were mixed of Zostera and haliduli, fringing salt marshes, and then oyster reefs. Now, there's a few ways that these habitats all differ from each other. One is the presence of that physical ecosystem engineer, or that 3-dimensional structure, where we have that on our oyster reefs, salt marshes, and seagrass beds. The other is the habitat type that's there. So we have our 2 flats, and then we have 2 plants, so they have root systems, and then we have oyster reefs that are our filter feeders. Elevation is also important, where subtidal habitats like subtidal flats and seagrass beds are inundated. Sediments are inundated all the time, while intertidal habitats, those sediments get exposed to the atmosphere every so often. So these physical differences will likely then lead to differences in the chemical environment, leading to differences in denitrification. So we measured denitrification rates at these different habitat types for 2 years. And what I have here on the next slide is then the annual rates of denitrification. These are N2 production. So we have our different habitat types, and you can see right away that seagrasses and oyster reefs both have high rates of denitrification. Our intertidal flats also have a higher rate of denitrification. These annual rates we got by actually taking our measured rates from the laboratory, and then we developed a model to extrapolate them to a year based on redox potential and inundation and elevation. Now that we had that yearly denitrification rates, we then linked that with habitat area to see what the total denitrification capacity was for the sound we were studying, which is Bogue Sound, North Carolina. And then we modeled the watershed nitrogen load to see how efficient these different habitats were at removing nitrogen, if they were really making a difference for nitrogen loading and removal and overall water quality in the system. So using all this information, we were able to determine the importance of those benthic habitats for that ecosystem service of nitrogen removal. Collectively, our results show that, in fact, a lot of the nitrogen load was removed by denitrification in this ecosystem. In fact, 76% of our estimated watershed nitrogen load was removed just through denitrification. So that's probably the reason that the sound has good water quality. One follow-up question that I get when I presented these data before is then, well, what habitat should we restore to increase denitrification capacity? And my answer is the habitat that has the highest annual rates of denitrification. And that would be the seagrass beds in the study. So converting the subtidal flats then to seagrasses would lead to an increase in nitrogen removal at the ecosystem scale. To summarize this section, we see that seagrass beds have high annual rates of denitrification. And that then if you want to increase the ecosystem level denitrification, you can use restoration, targeting those structured habitats that have been lost, because they provide more ecosystem services than, in terms of nitrogen removal, than the flats. They also likely provide benefits for other services like carbon sequestration, like habitat and for commercially available fish. That also might provide benefits as well. So I just told you that seagrass beds had the highest rates of denitrification, but seagrass beds are being lost. So what does all that mean? Zostera is the foundation species of global importance. Some of you are probably familiar with the ZEN Zostera experimental network that's designed to look at Zostera as a seagrass bed, seagrass species. And then what we're seeing is, this is data from Chesapeake Bay, where it's a key foundation species, is that Zostera's been lost in 29% in area and cover since 1991. In an analysis, John Leftek and colleagues, they looked at what these drivers for this loss could be, and they found that it was really driven by turbidity, so an increase in particulates in the water column, which limits light availability, which can affect seagrasses because they need light, and then also an increase in temperature. So associated with climate change. So in his analysis, he argues that it's likely that Zostera is very unlikely to recover in our future climate because of an increase in turbidity and the fact that the waters will continue to get warmer. In his analysis, he shows data that increasing heat will continue just to knock back Zostera because it can't keep up with that warming temperature. And that, in fact, within 2 years, when they had these die-offs in Chesapeake Bay, it actually could eliminate the entire seed bank for Zostera. So the seeds that are there that are ready to grow. And then what happens when we lose these seagrass beds, this Zostera, this foundation species? Is something else out there that could step up to the plate? I'd like to introduce you to Rupia. Rupia is also a seagrass. It's a little bit of a weedier grass compared to Zostera. It does have a thermal stress that it does handle warmer temperatures better. So when we get these die-offs and this increase in temperature, that stress conditions can support these opportunistic seagrasses like Rupia better than Zostera. So if we're seeing these large die-offs of Zostera and we're seeing this changes in temperature, this might mean that Rupia could come in and take over in some of this area. And in fact, that is actually what we're seeing. Here we have mean cover of the two different seagrasses. Rupia is the lighter green and Zostera is the darker green. For some time, it's been Zostera dominated. But then we have this crash. And then as we start to see the cover come back, it dies back again, and then Rupia starts to take over. So we actually see this inverse relationship between Rupia coverage and Zostera coverage. That means that Rupia could replace Zostera in these ecosystems. There's a few things about this that are interesting, and that the species are different. So they have different morphology and characteristics. And it's those differences that might then lead to the differences in ecosystem services or their role in the ecosystem. So I have here a table of some of the differences that might be contributing to that. For example, Rupia is short. Its canopy height is only about 10 centimeters. And its root system doesn't go very deep into the sediments, only about 5 centimeters. While Zostera has a big canopy, 20 to 50 centimeters, and its root system goes deeper into the sediments, almost double that of Rupia. Rupia has a higher shoot density per unit area than Zostera, and it can be more ephemeral than Zostera, so it can come and go and come and go. Rupia is found all along the east coast of the US, from Florida to Maine. And for Zostera, the Chesapeake Bay is kind of its southern limit. They also peak in biomass at different times of the year, where Rupia peaks in late summer and Zostera tends to peak in spring or in May. So our question was then, how do these morphological and structural differences between the seagrass beds affect the ability for seagrass meadows to remove nitrogen? You can see on this photo here that Rupia is over here, does not look as lush as Zostera does, which is up here. So in Chesapeake Bay, we were really lucky that these two habitats or two seagrasses actually form mixed beds, and they can occur in a small, in close proximity to each other. So to answer our question, we then went to one of these areas where both seagrasses exist. And we did this twice, once in the spring when Zostera was at its peak biomass, and then once in the summer when Rupia was at its peak biomass. Because I really like to measure denitrification, that is what we did. What I plotted here is actually our net N2 fluxes, because we don't measure denitrification directly, we measure this net N2 flux. So a positive net N2 flux means that denitrification occurs in excess of nitrogen fixation, when a negative net N2 flux is nitrogen fixation in excess of denitrification. So denitrification, remember, is that removal of nitrogen, the conversion back into N2 gas, while nitrogen fixation is taking that N2 gas and making it into a bioavailable form of nitrogen. So these two processes have opposing roles in the ecosystem, where we have removal and then a source of new nitrogen, essentially. So we went out to these habitats and measured our net N2 fluxes. We also had a bare reference sediment nearby just to kind of get at what the baseline conditions are. What are the benthos doing without the seagrass? And here are our results. Our spring is in green and our summer is in blue. I think the most striking thing for me when I looked at these data is that this Rupia shifts between net nitrogen fixing in the spring and then denitrifying in the summer. I think that this shift has to do with the fact that Rupia was entering its growing season. So it was trying to get more and more nitrogen to meet those nutritional demands. I also think it's interesting that Zostera maintains this denitrification capacity during both the spring and the summer. But that overall, Zostera does so because Zostera maintains denitrification, we see more denitrification with Zostera present. And when denitrification happened, or the net positive N2 flux, there was always this increase from bare. In fact, in the summer, the bare sediments did nothing. And then in the spring, they also had a net nitrogen fixation, probably trying to get at some of the available nitrogen. So what is driving these differences in these different seagrass beds? Do you remember denitrification is driven by three things: carbon or organic matter, nitrate availability, and oxygen. So we were able to measure sediment organic matter from our different sites in the same seasons, which I've plotted for you here. Zostera has the highest amount of organic matter compared to both bare sediment and to Rupia. We also saw, and then sediment organic matter had correlated with above ground and below ground biomass. Something else that Zostera is better at. So Zostera has that bigger canopy and that deeper root system. So there's more. I think that the organic matter differences are then driving these rates of denitrification that we are seeing. To kind of explain this, I put together a little diagram. With Rupia that has that shallow root system, we see oxygen availability, but not at depth. It kind of is just in the surface sediments. While Zostera has that deeper root zone, so we can see oxygen is more available at depth. And then we have organic matter. That organic matter floats in the water column, for example, and it just goes right through Rupia because it doesn't have that canopy to trap it, which Zostera does. So that organic matter hits the Zostera and it would settle on the sediment surface, leading to an increase in organic matter with the Zostera area compared to the Rupia area. So Remember that denitrification is regulated by organic matter, but also nitrate. Where do we get nitrate from? Well, it's either directly in the water column or through nitrification. So nitrification is the process where ammonium is transformed into nitrate. And in this area of the Chesapeake Bay where we were working, there was very little nitrate available in the water column. So all of our denitrification was actually coupled to nitrification. And nitrification requires oxygen. So with that shallower root system that Rupia has, the oxygen can't get deep enough to connect those zones of nitrification and denitrification. So essentially in the Rupia, you might have this disconnect between that coupling of nitrification and denitrification. While in Zostera, it's you can put the processes are more tightly coupled. At least that's my hypothesis. So nitrification is really the gatekeeper here, and that increase in oxygen availability at depth and coupled with that supply in organic matter is leading to an increase in nitrification, denitrification in Zostera compared to Rupia. I think collectively this indicates that Rupia does not sustain that same level of ecosystem function that Zostera does. And we've been losing Zostera, right? But I'm happy to report that there is hope. These are some data looking at Zostera restoration in Chesapeake Bay. And there was actually a goal set by Chesapeake Bay to restore Zostera. It's the target of their restoration goal. We can see that as time is progressing, restoration is keeping up or meeting this goal. It's on track. It hit the interim goal, and then a new paper that just came out last week sort of, again, demonstrates that they've been able to restore seagrass beds, Zostera beds in Chesapeake Bay through targeted and focused restoration. Something else has also happened in Chesapeake Bay, that they have had a targeted reduction in nitrogen loading through their total maximum daily load. They really want to stop nitrogen from entering Chesapeake Bay. So what we have here are two figures, the one showing the mean nitrogen concentration in Chesapeake Bay over time, and the other showing total seagrass area. And the trends are that there is a decrease in nitrogen and an increase in seagrass cover. So I think this means collectively we can say that active management, both for restoration and for targeting nutrients, can lead to a reversal of the human impacts on coastal ecosystems. So the connection between nitrogen and seagrass is also important to remember, that nitrogen causes or is linked to eutrophication. So by targeting that reduction in nitrogen loading, then we don't have as much algal growth in the water column, and we can have more light availability to the sediments for areas where seagrass lives. So nitrogen has sort of that important role in also affecting the availability of light for seagrasses that they need. So collectively, we're restoring seagrasses and reducing nitrogen, leading to overall increase in ecosystem health. Chesapeake Bay is not the only place where we're seeing this. In fact, Tampa Bay has a very similar success story and is probably one of the most successful restorations that I can think about when I think of focused management and the connections between nitrogen and seagrass beds. Very similar events happened in Tampa Bay as they did in Chesapeake Bay, where there was an increase in nitrogen loading, increase in chlorophyll, decrease in water clarity that led to seagrass loss. Targeting reductions in nitrogen loading and focused management and restoration efforts then led to an increase in seagrass area. And now we're continuing to see seagrass growth in Chesapeake Bay, or in Tampa Bay, I'm sorry. But this kind of begs this question then for me about what's happening to seagrasses for denitrification in Florida. So to answer this question, I went up to Cedar Key, where they have 3 different types of seagrass beds: Halidoli, Serengodium, and Thalassia. If we put this into the work that I was thinking about in Chesapeake Bay with the different species, we can see sort of same kinds of questions here. We're in the Gulf of Mexico, we're having an increase in temperature and we're having increase in nutrients that have led to changes in the coverage and distribution of different seagrass beds and different species. Shoal grass is being taken over and shaded out by manatee grass and turtle grass. So Serengodium and Thalassia are taking over Haladuli and is being replaced by different species. These different habitat or different grasses also have differences in terms of their morphology and in terms of blades, height, width, and then also just overall density within these beds. So all of these physical differences then could relate to differences in production, secondary, primary production, and then species richness and abundance, as well as other ecosystem functions that I'm after, like denitrification. So getting this first assessment of denitrification in these individual seagrass beds was really what I set out to do early on in my time in Florida. And I think that that information sets the baseline then for helping to target restoration. So we went out and measured denitrification rates, net and two fluxes again, at all of our different seagrass beds. What we found was that Thalassia, we also had our bare reference site because we always need to know what the baseline is. Thalassia increased denitrification by only 30%, and then Serengodium increased by 101%. So there was much more denitrification in Serengodium than in Thalassia beds. And denitrification didn't really do anything with Haladuli. It was just almost a net zero flux. So no fixation and no denitrification. So if we start to see then this shifting in species and a dominance by different species, will have consequences for this denitrification, this nitrogen removal ability of seagrass beds in the Gulf, but will also have consequences for fisheries and other ecosystem services. In conclusion, from this set of work, we found that Rupia does not sustain the same level of denitrification as Zostera, but that active restoration efforts can work to help recover ecosystem services, and that the morphology of seagrass species, whether that was in Chesapeake Bay or up in the Gulf, can influence the nitrogen removal ecosystem services that we get. Now, thinking a lot about denitrification, as I'm sure everyone can get that I think a lot about that. And now that I live in South Florida, where we're more in a phosphorus limited system, but I've been thinking a lot more about blue carbon benefits. And it's really led me to think about or look at some of these relationships between different ecosystem services that seagrass beds provide. So the third part of my talk is going to look at that relationship. I think most of us know what blue carbon is, but blue carbon is the sequestration of carbon and storage into sediments and biomass that is provided by coastal habitats like marshes, seagrasses, and mangroves. It's a really important ecosystem service in terms of mitigating climate change because it's taking out that CO2 from the atmosphere, fixing it, and then storing it. But there's a little bit of a catch here, is that there's also CO2 production that can occur within these different habitats because of respiration of organic matter. So there needs to be a balance. I think that that's why I like this figure, because you have that CO2 uptake, but it's also a reminder that these are also sources of CO2. So finding that balance is really what's important for making sure we have a blue carbon habitats. So carbon dioxide naturally occurs in the atmosphere, but then as it dissolves and is dissolved in seawater. Water and carbon dioxide combine to form carbonic acid, and that can actually dissociate into then the hydrogen ions and bicarbonate ions. So when you get more CO2 dissolving into water, that's when we get that change in pH. Because of human-driven increases in CO2 in the atmosphere, more CO2 is dissolving into the ocean. So the ocean is currently about 8.1, which is a bit basic or alkaline. But as the more and more CO2 is absorbed, the pH will likely decrease and the ocean will just become more and more acidic. So DIC is dissolved inorganic carbon, and it is the pool of carbon that is CO2, bicarbonate, and carbonic acid. So as you would see the oceans or the coastal areas become more acidic, you would expect there to be more DIC. Total alkalinity is the opposite of DIC. Total alkalinity is basically this buffering ability, so the ability for that system to take on those extra hydrogen ions that wouldn't affect then pH. Total alkalinity is produced in vegetated habitats and can be that sink for CO2, but only when it's produced in excess of DIC. So total alkalinity is often generated by denitrification during that breakdown of organic matter. And because denitrification can produces protons, that's where we get that extra alkalinity from. So it's important then for the alkalinity to be measured with DIC to see if there is some sort of buffering ability that vegetated habitats have with regards to ocean acidification. So this has led me to my new question, which I've just started to really explore and dive more into, is are sediments in tropical seagrass meadows net sources or sinks of DIC, total alkalinity, and how much of that can be explained by denitrification? This is part of a larger study I'm working on to assess the potential for net total alkalinity production as a long-term carbon sink in seagrass meadows. I'm only going to talk about the part of the study today that I did, which was measuring the sediment-water fluxes of N2, total alkalinity, and DIC. Our ultimate goal is to place these in the context of water-air CO2 exchanges that we've measured with eddy covariance towers. This study was done in Florida Bay, which is a tropical seagrass system. So the sediments are really different than what I was working with in Chesapeake Bay, because this is a carbonate system. And in fact, this is exciting for me because most of our work, when we think about denitrification and nitrogen loading in general, has been done in these temperate areas. So getting to do some tropical work offers this whole new avenue to explore. So we went to two different seagrass beds. One was high density, and then the other was low density. And we collected a bunch of sediment samples around them, in them, and our cores did have, our samples did contain seagrass biomass that related to the density of these different sites. We also had bare sediments. So those were sediments that did not have any above ground or below ground biomass, and collected sort of from these bare patches within this, within these different meadows. And then we measured our fluxes for N2, O2, DIC, and total alkalinity across the sediment-water interface using flow-through core incubations. And here are our results. So what I have here are our different sediment types. So our bare, our high-density seagrass bed, and low-density seagrass bed. And then we have our samples where there was seagrass present and seagrass absent in the cores. And we have our total alkalinity flux, our DIC flux, and our net N2 flux. Think right away, something's happening here. And that relates to the presence of the seagrass bed, there's seagrass biomass in the cores. This blue is higher than green in most every case, suggesting that there's something happening with the seagrass biomass there too, whether that is oxygen pumping through the root system or just that community that's around the blades. For denitrification, fluxes were really low for our seagrass beds and near zero in some instances. And then even though this one's higher here at the high density, it's actually really low compared to the flux numbers that I've measured from other seagrass ecosystems. If we look at total alkalinity and DIC, we see that the sediments were also a source of both total alkalinity and DIC. which means that the sediments are both producing acidity through DIC and also alkalinity through total alkalinity. So because the alkalinity is being produced, there's a chance that the DIC production, or that that acidity, is actually offset by total alkalinity. Essentially, these sediments are then buffered to that change in DIC. In the context of blue carbon, this is important because we can use literature values to figure out the total carbon burial that these sediments should have. And in doing that, we actually found that our DIC fluxes are greater than that. So without that ability for those sediments to also produce total alkalinity, overall, our sediments or seagrass beds down here would be a net source of CO2 to the atmosphere and not a blue carbon sink. Luckily, they're also total alkalinity sources, and that is they're essentially buffered then. When I set out to do this study, I was more interested in this relationship between total alkalinity and N2 fluxes and denitrification, to see if denitrification was really producing that total alkalinity like we expected it to do. And in fact, we found no correlation between total alkalinity and N2 fluxes. I think something else is driving those total alkalinity fluxes, probably sulfate reduction or sulfide oxidation. And then also carbonate precipitation and dissolution may contribute to that total alkalinity and are probably larger sources of the total alkalinity pool than denitrification was. We have data on all of that, we just don't have it back yet. So stay tuned. So in conclusion, I think from this work shows that denitrification increases with the seagrass biomass in the cores, but denitrification was pretty much near zero in this at this site, and in balance with nitrogen fixation, and competition with sulfide inhibition might be leading to this decrease in denitrification that we saw in Florida Bay cores compared to other locations. The sediments were a source of DIC and total alkalinity, but that wasn't correlated with denitrification. So something else is driving that total alkalinity, and that it's important that the total alkalinity is there because that's buffering the DIC release. That is actually allowing these sediments to be blue carbon systems then. This work overall makes me get really excited about this coupling of biogeochemical processes between our denitrification that I think about and measure a lot and has this value for nitrogen removal, but also this blue carbon and carbon storage, carbon sequestration potential. So overall, I have a few take-home messages. The denitrification does differ by different habitats. So not all, you'll get different rates or different nitrogen removal if you restore seagrasses, or if you restore oyster reefs, or if you restore marshes, and that has implications for overall nitrogen budgets. Morphology of seagrass species does influence the ability of these species to remove nitrogen, so that's also important, and that has implications for climate change, with climate change as we see shifts in distributions. And then overall consequences for the ecosystem functions and services that we expect from seagrass beds. Vegetative sediments, such as those seagrass beds, can help increase the buffering capacity of our coastal waters, which is important as waters are getting acidic. And that there is the ability for management efforts, targeted management efforts, to reverse human impacts on coastal ecosystems. Ultimately, the information that I generate, I hope, will aid in providing some reference to more effectively manage and conserve coastal ecosystems and the ecosystem services they provide, especially in the context of climate change. So with that, thank you for your attention, and I'll be happy to take any questions.
Thanks, Ashley. That was excellent. You took us from the core scale to the whole Chesapeake Bay scale, and gave us some worrisome trends and also some positive trends. So it was like a big budget Hollywood thriller. We really appreciate it. So thanks a lot. We'll open it up to questions from both the Zoom room. We did have a question from Rupesh Bomia about temperature effects. And he asked whether you were going to show some Florida results. You eventually did, but maybe you could answer more broadly the question about there's climate change buffering from blue carbon storage, but there's also just warming that's baked into this pie of humanity on the earth right now. So thinking about warming and denitrification rates and carbon, and it would seem as simple to say if we're warming, we're going to denitrify more, but I'm sure it's not that simple. Can you talk a little bit about where we think warming is going to take us?
Yeah. Yeah, it is simple to say that denitrification is going to increase. All these rate processes will increase, but you're going to have other consequences too. So it's sort of, what does that do? Like if you have more and more organic matter production, that's also a consequence of too much of increases in temperature, and you increase metabolism, then that has consequences for oxygen availability. So more anoxic conditions. So it's just a bunch of different feedbacks that can get upregulated or downregulated.
Thanks. We also have a question from Elliot White from the YouTube. Do seagrasses have the ability to handle increased nitrogen loading from freshwater, wetlands, and uplands experiencing saltwater intrusion? Well, I know Elliot has a bias about this process of saltwater intrusion, but yeah, so as you're fluxing a bunch of carbon, organic matter and nutrients from saltwater intruded soils, can they upregulate denitrification and take care of it?
I don't know. So some of my work looking at saltwater intrusion in particular in wetlands, not in seagrass beds, show that with saltwater intrusion, you actually get more DNRA, which is a recycling of nitrogen rather than a removal. It's a process that competes against denitrifiers for available nitrate. And saltwater intrusion, like saltier, will make that process kick on because there's more sulfate there. Seagrasses and mangroves are already in pretty salty systems, so that might not be, we might not see that same effect there. But I think that as you hit that saltwater intrusion and that freshwater pulse, you get that deposition of organic matter, then that's really what's going to start to drive some of these rate processing in these like land-water interface systems.
Thanks. Andrew, I see you on here. You have a question for Dr. Smyth?
Yeah, so it was a nice talk, Ashley. So I just have a question. So we talked a little bit at the beginning of you talked a little bit at the beginning of your presentation about temperature increases and how that might be bringing rupia into the system as Zostera kind of leaves the stage, possibly in some areas. I mean, where restoration hasn't been successful, but I'm wondering if there's a possibility of thalassia to move up. Like, I don't know what's setting its northern range limit. I probably should, but I'm just wondering what the potential for it to like move up the Atlantic coast is, or if you're.
Yeah, I'm not a seagrass ecologist, so I'm not actually. I don't actually know what the potential is for that either.
Yeah, it's
so,
not there yet, though. It sounds like. I think it's. I mean, it seems like it's within striking distance because I think its northernmost range is perhaps. Well, I don't even want to speculate, but yeah, I don't know if there's been any talk in the Chesapeake about that potential. For it to get up there.
About thalassia getting all the way up there? No, I haven't heard anything about that. So,
okay.
But I think with tropicalization, we're going to start to see all these tropical habitats move north. So we have to get ready. I think that the lessons that we learned from Florida are then really valuable for other places because we have all that here already, and they're, we're kind of setting the stage. So. I've been asked by people like why I'm doing any of this work in Florida because it's all going to be underwater soon anyway. And that's my answer, is that like we need to know what happens here to make informed decisions in the future.
Yeah. One other question I just had too is related to the measurements that you made on denitrification as well as these other processes. They come from these habitats that are this comparative approach you took in the Gulf of Mexico, which is really nice, comparing, the three different kind of major seagrass types. But I'm just wondering if the differences that you might have seen between areas dominated by those three different types or the bare sediments had perhaps some underlying differences that contributed to the fact that they're dominated by one of those species, and how that might have factored in. I mean, I'm sure it's something you thought about, but curious to get your thoughts.
Yeah, it's definitely, it's what the discussion's for, right? It's definitely something that we think about, or Laura and I have even talked about, like the habitat use. So who's there, what's there, that can contribute to some bioturbation activity, movement of organic matter. Some of the other like differences just from the work that she's on with like diversity and population genetics, what role that might play into things. Aside from the obvious, which is like depth, depth can really be important for denitrification, and these seagrasses tend to occur at different depths. So,
right. Okay. Yeah. Thanks.
Mark, do you have a question?
Yeah, I've got a quick question. A great talk, Ashley. It's kind of exciting to see which way you're moving now. I'll be interested to see some of your added results. But my question is related to denitrification and also nitrogen fixation, and how the ambient nitrogen levels, either as inorganic nitrogen forms or organic forms of nitrogen, which seem to be possibly the actual source of the nitrogen that gets ultimately broken down and then nitrified and then back out again. But how do those influence your rates, or do you have a feeling for that? I mean, it probably relates more to some of the earlier work, but obviously the nitrogen fixation is a energetic process, and so if there's excess nitrogen or available nitrogen, it seems like that shouldn't be quite as dominant a function as perhaps the denitrification side of things. I'm just curious, in the context of your rates, how much do you see that ambient nitrogen being a big driver of the denitrification side, in addition to what you've already identified as variables between community type?
Yeah, no, it's a huge driver. We do see more nitrogen fixation, net nitrogen fixation, when we have lower ambient nitrate concentrations, for sure. And then we've been doing our experiments where we like pulse nitrate through the systems to see what the response would be then, to see if we can shift these into denitrification in some instances. And sometimes we do, sometimes we don't, and we actually shift on DNRA instead. But I think like there's a really good point there too, Mark, that we kind of expect denitrification to happen in areas where there is already a lot of nutrients. And it's going to be this like solution to that because it can remove. I don't know if we always get that denitrification capacity where we need it. We can get denitrification further down, but what's happened down the estuary, but what's happened above, and if that's really where we need that nitrogen removal.
Well, and that kind of goes back to this larger context, and you showed two examples, one Chesapeake Bay and one Tampa Bay, where we have these processes in the environment that are helping us, if we want to think about it that way, to remove this excess nutrient. But from the standpoint of allowing those systems to function at a high level, we really need to be back to the sources and trying to reduce the application, number one, intercept that as quickly as possible, kind of the treatment train idea, before it gets into the natural system, so that natural system can maintain its optimal function to essentially buffer for those loads. So, I mean, I think contextually they're great examples, but it's not just let's hope for the natural system through these processes. Like you identified, maybe you're getting 76%. Well, but maybe we get 100% if, under, more healthy conditions or something like that. And so either way, great talk, but curious to see where you go with the additional information too.
Awesome. Thanks so much. We're over now, so I will ask you all to help me give a round of applause to Ashley Smyth for her talk today, either in real life or in your fake there, little icon there. Very good. We really appreciate you coming to give us a talk today, and look forward to the next work, and look forward to talking to you more soon. Thanks, everyone. Students, make sure to send in your one-page summary. And we'll see you all next week. Thanks so much. Mark, if you want to stay on. Sorry, it's always a little weird and awkward to end these things. The recording is